My name is Roland Croft, and I am part of the CREST research group at the University of Adelaide. I'll be presenting our paper, Noisy Label Learning for Security Defects, on behalf of my co-authors Ali Bapa and Huaming Chen. The continual advancement of AI has led to the growth of data-driven methods for software development and quality assurance. For instance, GitHub Copilot is a recently released smart programming assistant that helps developers write code, and it doesn't stop there. These AI-based solutions are achieved through the large abundance of open-source software development data and artifacts that can be used to train and fit intelligent machine learning models. A particularly difficult software quality assurance task that we wish to automate is software vulnerability detection, where we use previous examples of vulnerable code to help predict on future software. Many researchers have made great strides towards prediction models in this direction. However, these models currently remain theoretical due to data challenges. We can only use known vulnerabilities to train a supervised learning model, but in reality, there are a much larger number of undetected or unreported vulnerabilities concealed in the unlabeled set. We can show this through a simple real-world example. Figure 1 here displays the decision boundary of a classifier trained only using knowledge of known vulnerabilities at the training time. However, as time goes on, latent vulnerabilities that were originally unknown are uncovered. Figure 2 displays a sample of latent vulnerabilities that were discovered using an additional 3-year inspection period, and we can see that the decision boundary significantly changes when provided this new knowledge. Unfortunately, it's largely infeasible in practice to obtain a completely noise-free security defect dataset. Non-vulnerable modules are difficult to be verified and determined as truly exploit-free, given the limited manual efforts available. Hence, we turn to noisy label learning methods that aim to produce classifiers robust to label impurities and leverage the most from limited label data. Our study attempts to tackle this issue by investigating some characteristics of label noise in software vulnerability datasets and the ways that we can potentially mitigate its impacts to produce more robust, trustworthy, and reliable software vulnerability prediction models. We achieve this through a case study of a vulnerability dataset that we manually acquired from the Mozilla Firefox project. We first identified all disclosed vulnerabilities that would be available at model training time, and then we manually examined the remaining unlabeled files to detect latent or undisclosed vulnerabilities which did not receive a proper label from the known vulnerability reports. I stress that it's largely infeasible to obtain perfect knowledge of the noisy labels due to the highly difficult and effort-intensive nature of this task. We instead only provide a partial view. Finally, we trained a software vulnerability prediction model on these datasets and applied a variety of noisy label learning techniques to attempt to see the degree to which we could remediate the impacts that noisy labels have on a classifier. Firstly, we inspected some characteristics of the noisy instances that we were able to identify. Table 1 here displays the total number of files collected in our dataset and the number of which had reported vulnerabilities. For noisy labels, we manually identified fixed bugs that were improperly assessed as not security relevant, that is, silently patched. We also collected latent vulnerabilities by backtracking code in future vulnerability reports and determining vulnerabilities which would not have been known at model training time. In total, we collect over 4 times the amount of noisy labels in comparison to the clean labels. For the latent vulnerabilities, we also documented the average number of releases for which they remained latent for to indicate the level of noise. We find that it significantly differs for different vulnerability types, which implies that the label noise is likely to be feature dependent. We then examined the impact of label noise and whether we can use noisy label learning techniques to mitigate the impacts of this noise. As a baseline, we simply consider the default case in which we train a vulnerability prediction model without any knowledge of the noise. Then we consider a semi-optimal ideal case in which we do have partial knowledge of the noise via our manual cleaning. However, this wouldn't be feasible in a real-world situation, as it requires future knowledge unavailable to us at the training time to identify these latent vulnerabilities. We can see that the label noise has a significant impact, as the extra knowledge in the semi-ideal case significantly improves the performance. Finally, we investigated multiple different noisy label learning techniques, but for brevity I will only describe the best performing technique here. Two-stage learning uses the geometric distance of the embedded features to determine which non-vulnerable labels are most likely to be reliable, as they are the furthest distance from the reliable vulnerable labels. We consider the remaining unlabeled files as noisy, and then train a model using the reliable vulnerable and non-vulnerable samples to classify the remaining data points prior to the inductive learning on the test data set. In terms of performance, all the noisy label learning techniques were able to improve the performance of the baseline, despite not having any additional knowledge of the noisy labels. The two-stage learning approach significantly outperformed the baseline, but there's still room for improvement, as it couldn't quite match the performance of the ideal case. In conclusion, we found label noise to be a very prevalent issue in software vulnerability datasets, but it's quite difficult and even infeasible to be cleaned. However, we can remediate this issue at a model level by using noisy label learning techniques. Our best performing method improved the AUC and recall of baselines by up to 8.9 and 23.4% respectively. More details of our study and our findings can be found in the full version of our paper.